Suspension Bridges with Parabolas by Nolan Simon. The suspension bridge uses parabolas within the cables of the bridge that resemble a curve, as seen in a parabola. The suspension bridge's parabolic shape ensures that the bridge is stable and can support the cars that are on the bridge at the same time. It's like insurance for bridges. The curve of the cables is because of both gravity and compression, also known as tension forces. The bridge has multiple cables, one on both sides of the bridge, to distribute the heavy weights of hundreds of cars that are all on the bridge. These bridges were invented in the 16th century when Francisco Pizarro and his army of Spanish conquistadors came to Peru to conquer the Inca Empire. As you can tell, there are many ravines and bodies of water in Peru, and the conquistadors needed a way to travel large amounts of people across. They decided to tie large pieces of grass together for extra support. The first bridges could only span about 150 feet, with grass cables, but as time continued, it was later reinforced with steel chains in place of the cables. Nowadays, these bridges are known for their low construction cost and ease of maintenance. Their parabolic cables allow bridges to easily span over 2,000 miles. That's farther than 66 times how far the average human being can see. Without these cables, a bridge can only be able to span about 1,656 feet. The suspension bridge has benefited humanity by giving humans a way to travel over extremely large lakes and gaps. Without these cables, it would be nearly impossible to cross over places like the Grand Canyon, the Royal Gorge, or to the San Francisco Bay.
Dennis, we're supporting, let's say the book weighs 1 kilogram.
Okay.
How much force are you exerting on your side?
Half a kilogram.
And I'm exerting half a kilogram on my side.
Mm-hmm.
Have you ever noticed that suspension bridges always sag like that?
Yeah, they always have a curve.
Have you ever had clothes on a clothesline? The clothesline always sags like this. Or a chain between two posts, never goes straight across, always sags. Well, that's based on a very important scientific idea called vectors. Have you ever heard of vectors?
No.
Well, scientists diagram forces by the length of the arrow and the way it points. That is a sort of indication of how much force is applied. Hold your end again. In this case, when we pick it up like this, half a kilogram on each side, assume, there'd be an arrow that goes up like this. An arrow going down like this for the book, and an arrow going like this for the fact that it's suspended.
Okay.
But now as we start to move the two supports apart, that vector still has to be 2 pounds over here, but we're now applying it at a great angle, aren't we?
Mm-hmm.
All right. And the more we apply it at a great angle, the less force there's going to be there. Hold it nice and level now. Okay, pull. Get it straight. All the way. I'm pulling you. We still haven't got it straight.
No.
Let's do that again. This time with some sort of a scale in the middle so that we can see. Here, you hold that rubber band. I'll hold this one. Now the rubber band on each end is going to sort of represent the amount of force we're applying.
Oh.
The more it stretches, obviously, the more force.
Right.
Okay. Let's do that again. Can you hold it up a little higher so it's off the table? Okay, you can let go of your other hand there. Okay, now pull. See what happens to the rubber bands?
Yeah, it's stretching quite a bit.
Stretching like crazy. And we're putting a great deal of force here, but obviously not enough to counteract 1 kilogram in the middle. We could go like that, and eventually we break the rubber band.
Yeah.
And that's why suspension bridges are always sagged like that.
The rubber bands that he put on each side of the rope act as cables in the suspension bridge. The bands allow the bridge to hold more cars, allow for more flexibility, and increase the length. This is how the bridges are able to span such large distances. In the diagram that I have drawn, it represents the suspension bridge's cables in the form of a parabola. The equation for this particular parabola is y equals 0.13x squared plus 0.1. I got this equation by inserting the drawing of my parabola into the graphing calculator Desmos, and then by adjusting slider A, slider B, and slider C until they match the parabola in my drawing. Thank you for watching.